You're also going to see examples where we use powers of I. So what I'm going to do here is show you the four main powers of I that we're going to use, and then you can use these four to help you find I to any exponent. It could be I to the 500th, and you'd be able to reduce it down. So we're going to just start off with I to the 0 power. If you remember from exponents, as you've learned them, anything to a 0 power will always be 1. So I to the 0 is the same as the number 1. I to the first, we can just rewrite that as I. Okay. But then when we get I squared, remember that when we square something, this is the same as saying the square root of -1 to the second power, because remember I is the square root of -1. And a square root and a square cancel each other out. So this would reduce down just to -1. So I squared is equivalent to -1. And then I to the third, we can rewrite it with different exponents. We can rewrite this as I squared times I to the first, because 2 plus 1 is 3. So then I can simplify that. We just said I squared was the same as -1. And then I to the first is just I. So when we multiply those together, we get -I. So I to the third is equivalent to -I. Okay, so these four right here, 1, I, -1, -I, are going to be the main four answers you use anytime you have exponents with your imaginary numbers. So if you check this, if I look at I to the fourth, that's the same as writing I squared times I squared. And remember, we just said I squared was -1. So that's -1 times -1, which gets us +1. And notice now we're back at the beginning and we've repeated. So I could rewrite I to the fifth as I to the third times I squared. 3 plus 2 is 5. That's how we know that we've split it correctly. And we know that I to the third is a -I. And I squared is a -1. So this gets us +I, which is the same as I to the first. So notice that these here I've highlighted in blue are the same, the purple ones are the same, and then this one means that the orange ones will be the same. So I to the sixth is the same as I squared, which is -1. Okay. And if I tried to find I to the seventh, I could continue with this pattern, 1, I, -1, which means this would also be -I. And you could check it. You could break it up into 3 I to the third times I squared times I squared. So here I could show you that. I to the third times I squared times I squared. Because 3 plus 2 is 5, plus 2 is 7. And then I could replace these with all their simplified versions, and what you'd end up with is -I. Okay. So instead of having to break it down every time, because we know there are four main rules, that's these here, that you would need to make sure you know and you memorize. If you can tell me those four, then we can use those for any exponents that I ask for with I. For example, if I have -5I times 3I, I'm going to go ahead and multiply those together, and that would get us -15I squared. And then I know from the last page that I squared was the same as -1. So this is the same as -15 times -1, which is +15. So there's my simplified version. And then we can also do this with higher exponents. In example 3, it says simplify I to the 31st. So rather than trying to break 31 up into multiple smaller exponents, which you could do, but it would take a while, instead, we know that there were 4 different options. So what we're going to do is take the exponent and divide it by 4, since we had 4 options, and we're going to figure out what our remainder is. So if I go ahead and divide this, I know that 4 goes into 31 7 times. I go ahead and subtract, just doing long division. I get that my remainder is 3. So what that means is that I to the 31st is the same as I to the third. And if you look back at our last slide, we said I to the third is the same as -I. So that means I to the 31st, when reduced down, is equal to -I, and we'd be done. Okay, so any exponent can work. You just have to know to always divide by 4 because there are 4 options, and then whatever remainder you get is going to be the exponent of our 4 that you match. So I would go ahead and, if you want to try this one, I would try to reduce down I to the 53rd. So divide 53 by 4, figure out what your remainder is, and then match it to one of the 4 that we talked about in the last slide. The last part of our imaginary numbers are what we call complex numbers. And I went ahead and wrote an example here for you where it says 5 plus 3i. So a complex number is made up of 2 parts. The first part here is the real number, and then the second part here is the imaginary number. So in order to be a complex number, it has to have a real number and an imaginary number added or subtracted together. And so examples of this might look something like -1/2 minus 4i, or 2 minus 3/4 I. Lots of different variations as long as it's got a real part and an imaginary part. The other thing you might see are what we call pure imaginary numbers, and those are when they don't have a real number. For example, the number there would be 0, and those might look like this: -2i or 5/3 I, anything that just is an imaginary number with no real number added or subtracted to it. Okay, and these complex numbers are used in electrical problems, so anything that might be involving voltage or current, impedance, things like that when you're doing calculations. And a lot of times you'll see them use the letter J instead of I, just to keep their letters and variables straight. But here we're going to be mainly focused on using I when you're doing your typical imaginary number problems. So our examples that I want to go through today are where we're going to use these complex and imaginary numbers to do addition and subtraction, and then we can also graph them real fast. And the last video is going to be over multiplying and dividing them. So to add and subtract complex numbers, it's really easy. You basically have to just combine like terms. I've got the example here that says 5 minus 7i plus 2 plus 4i, and we're literally just going to combine the things that go together. So the real parts, 5 and 2, if I add those together, are going to get us a 7. And then if I add the imaginary parts together, -7 and 4i, when I add those, I get -3i. So there's my final answer. And if I want to graph that, we're going to think of it like graphing a point. The difference is that instead of just graphing an x and a y, we have 2 different axes, the real axis and the imaginary axis. So on the real axis, we're going to look at the real number. So that's going to be 7. So we'd go over to +7. And then the imaginary number, which would be like our y-axis, would be -3. So we'd go down to -3i. So this complex number would be right here, 7 minus 3i at this point. Okay, so when you graph a complex number, think of it like graphing an ordered pair. Same concept. So go ahead and try this example here. We have 4 plus 6i minus -1 plus 2i. So remember, you're combining like terms. Be careful with the subtraction. And then when you're done, I would encourage you to try to graph it. Remember, the x-axis is like the real numbers. The y-axis is the imaginary numbers. And that's it. Next video is over multiplication and division, so if you have any questions, just let me know in class. Thanks for listening.